Welcome everybody to our journal club in biomechanics. And this week we are going to have a presentation by David Nordsletten, who's going to talk about a viscoelastic model for human myocardium. And we just like to thank my co-hosts, Emma Lejeune, Matt Bercy, Johannes Wackemeyer, and Manuel Rausch. And just a reminder that this and all of our previous journal club sessions are available on YouTube, so please check them out. And then without further ado, David, if you can talk to us about a viscoelastic model for human myocardium.
Sure. Yeah, it's great to be here. It's been fun hearing the other talks in this journal club. I think it's been really successful, and it's cool to see all of the work going on in biomechanics. And so it's a pleasure to be here to talk about what we've been doing in terms of viscoelastic mechanics in the myocardium. My group in general, we're interested in the heart. Let me just make sure I'm going on the slides here. There we go. And particularly we're interested in heart failure and heart disease. And this is really an interesting biomechanics problem and fluid mechanics problem in many ways. You have a very complicated environment, complex etiology for patients, and a lot of variability. And the disease really spans all scales that you see in the heart, from things that are all the way down to the micro scale up to the whole organ. So you can see the progression of disease at various levels. And my team, we've been focused principally on looking at the tissue level and the whole organ level. And what we do a lot, the kind of core focus of the team, is looking at this interplay between biomechanics, biomechanical modeling, and imaging. And so how do we take biomechanics principles and somehow combine them with imaging data in order to understand more about heart function or cardiovascular disease of different kinds? So that's kind of where we're coming from. But today, what I want to focus on is viscoelasticity in the myocardium. And part of this talk is really talking about fractional viscoelasticities, because that's kind of the core of the model that was presented in this paper. So I want to talk a little bit about that. Looking at viscoelasticity, there's a lot of evidence of this that's been published in the literature. Pretty much every study that you look at, you can see evidence of rate-dependent effects, hysteresis, stress relaxation. And these are just a few of the papers that you can find. We did a pretty thorough dig around, and I think the earliest works that I saw, this was not in myocardium, but it was in skeletal muscle back in the late 1800s. And there you could already see viscoelastic effects in the tests of skeletal muscle that they were doing. And there's some really interesting studies that have been published. If you keep digging around in the literature, there's one paper from the 60s where they looked at tortoise hearts, and they had these things ex vivo beating in a cylinder, and they're measuring the pressure and how it would change if you introduced a sudden bolus of fluid into the chamber. And what you could see are these little real-time spikes as they inject extra fluid, and then this relaxation over time as the heart's beating. So that was really kind of interesting to see. But this is kind of getting ahead of where I would like to be. And what I want to do actually is to give a little bit of a story behind this paper, where we came from with this. And really, our interest in viscoelasticity stemmed from our engagement with imaging, and that was looking at particularly elastography. And that's how we got interested in this idea of fractional viscoelasticity, which I'll talk a little bit more about later. Then when we started seeing that and that use of that type of model in the elastography community, we thought about how could we actually use that, and should we use that in what we do in the modeling world. And then kind of once we got our head around those questions of can we do it and should we do it, we started to think about, well, how do we actually do this for human myocardium? So I basically want to walk you through kind of our path to this paper, and then I'll tell you about the paper itself. Okay, so as I say, for us, this started with elastography, and I don't want to dive too much into this, but I'll just give you a little bit of an idea. So elastography, we're particularly interested in something called MR elastography. So this is basically doing elastography, but in the MRI. And the idea of elastography is pretty simple. So what you're doing is you're sending waves through a material, and then by looking at the motion of those waves, you can infer something about the biomechanical properties. And in particular for MR elastography, you send in these periodic, so basically sinusoidal small amplitude waves, usually between somewhere around 10 to 200 hertz, and then you image them. So just to show you an example, this is a cross-section of a torso here, and what we see is a liver. And what you'll do is you'll stick a transducer on the torso, and this transducer will vibrate, and that vibration will send small amplitude waves through the torso. And because you know exactly how you're pumping those in, you know the period that these waves are being pushed into the tissue, you can record the displacement of these waves in space and time. So you get these nice movies of waves propagating through the tissue. And in this case, we're just looking at the waves that are within this liver here. And what you can see in this case is already the wave is changing dramatically as it moves through this tissue. And that's because there's a massive tumor here. And the tumor has different biomechanical properties. So you can basically do a reconstruction and get an idea of what the local tissue properties are within the liver or within the tumor here. And you can see that in this case, it actually has a necrotic core in the center of the tumor. So this is a technique. It's been used for a range of different tissue types and is used a lot in research. And it's something that we were interested in because it's a great example of biomechanics integrated with imaging. So we wanted to look into this. And just to give you a bit of an idea of how this works. So basically what you're doing to get these maps of tissue stiffness is you record these wave motions, and then you use periodic linear viscoelastic wave equations. So basically this is a linear elastic material model. And what you assume is that you're in some periodic steady state. And because from the MRI, you're recording the displacement over time, you can get this displacement here, U. So this becomes a known in space. So you can take the field, you can take its gradients, and then the only unknowns that you have are this stiffness parameter G and this pressure. And so if you can apply some tricks, usually this is, doing things like taking the curl or coming up with some other clever ways of eliminating this pressure term, then you end up with only two terms that are in your momentum balance, and that's the momentum itself and the stress. And because of the fact that you're working at higher frequency, these momentum terms are not negligible anymore. And so they actually have a meaningful balance with the stresses. So that's how you can get to these stiffness maps here. And so we were working on this. We were looking at different ways in which you can develop reconstruction techniques that are maybe more stable, that use maybe more kind of robust methods. In this case, we were looking at effectively virtual fields. Then we were interested in how this interplayed with standard nonlinear biomechanics. So what happens now if you start to deform materials and look at wave motion? Do our equations that we come up with from a nonlinear mechanics perspective, if we linearize them locally around a large deformation state, is that really what the wave looks like? And we were able to show that that is kind of what you observe. And then also we've been recently looking at anisotropy. So how do these waves move through an anisotropic material? But when we look at this in the heart, this is kind of what we see. So this is the first images that we got in the heart. This is an ex vivo porcine left ventricle. And you can see the waves moving here. And what you observe is actually very clearly viscoelastic effects. And the reason why you can see that just by looking at this wave is that it has the appearance that the wave kind of moves around the heart as it goes. And if you look at just a simple 1D scenario of what a viscoelastic model looks like, if you have no viscosity, you get this sort of weird looking wave that basically undulates up and down, but it doesn't give you this idea that it propagates. And so as you add viscosity, you get this appearance of propagation of the wave through the tissue. So it's clear that this is there, and we needed to somehow account for it. And if we wanted to integrate these sort of elastography techniques with biomechanics in the myocardium, we needed to somehow merge these worlds. And when we were digging around and talking to people in the elastography community, they were very much in favor of something called a power law. And this is because when they look at, these are all just examples of different studies that have shown this, but what they see is that essentially the stiffness properties that they observe have a frequency dependence, and that frequency dependence seems to be related to a power of the frequency itself. So if you look at taking the frequency omega and you raise it to a power alpha, then that gives a pretty good fit of the data that they tend to get in these experiments. And so if you look at this,
sorry, quick question. Is that entirely phenomenological, or is there some sort of like mechanistic motivation behind that?
There is a mechanistic motivation, but yeah, initially it's coming from just observations of the experiments. Okay, so we have this sort of proportionality between the stiffness parameter that they measure and the frequency. And if you write that out in the frequency domain, then our complex stress tensor is basically related to this now G, which has a parameter dependence on omega to the power alpha. And if you go back to the time domain, then you can actually kind of bounce back and forth between these two models. And this is how you'd represent this power law behavior in the time domain. And what you end up with is this term here, which is actually the fractional derivative. So this is not a first order derivative unless alpha is 1. So if alpha is 1, then it behaves exactly like our standard time derivative. If alpha is 0, then it's basically no derivative. And anything in between, it has a dependence on the history. So it's basically giving you a power dependence on history over time. And the sort of theoretical idea behind this is that this is a way of capturing a hierarchy of distributed relaxation phenomena. So if you have a bunch of different relaxation times that are spread out and weighted over time, then this is basically an efficient way of representing that sort of hierarchy. So this was really kind of a popular model in that elastography community. And we were thinking, okay, is this really viable and extendable to nonlinear biomechanics? So can we bring this idea into that frame? And so this kind of got us started thinking about, can we do this and should we do this? And so the first thing we wanted to look at is, logistically, what is this going to look like from a computational perspective? So if we want to actually use this for simulations, we need to know that we can efficiently use these types of techniques. And so the first thing we did was we looked at just a simple linear viscoelastic setting. So this is basically our mass and momentum balances for a boundary value problem. If we thought of a forward problem in time. And if we look at the linear elastic or viscoelastic stress tensor, we get something like this. And what we need to be able to do is somehow approximate this fractional derivative here. Okay. And that becomes the key part, is how do we actually approximate that in order to do a forward simulation. And if we look at this Caputo derivative again, what you can see is it's basically an integral over time. So it depends on the behavior. If we're trying to differentiate this function f, then it depends on the behavior of f over all time. And that really presents some challenges if you're thinking from a computational perspective, because then you'd need to be able to have access to the behavior of your solution, not just at the current time step, but every other time step that you've had before. So we needed to come up with some ideas on how we could approach this. So we were looking around in the literature, and there are kind of two different strategies. There's a cumulative strategy and a recursive strategy. So the cumulative strategy basically looks at approximating this integral. And an example of this is the one published here. And we don't need to get into the details of the formula here, but the key thing I want to point out is just that you end up with a sum over all the time points here, which are represented by n. So in order to compute what the behavior of this derivative is at the time point n, you need to go back to the beginning and sum all the way up to the current time. So if you think about what that means from a computational perspective, then your accuracy, you might be able to get good accuracy, but you're going to have a computational cost that grows like the number of time steps squared. And you're also going to have a data cost that grows like the number of time steps. And so both of these things are really non-starters if you're thinking of doing simulations, complex biomechanical simulations in the heart. All right. So the other approach is to take a recursive approach. And this was really kind of pioneered by Juan and Agarwal in 2002. And the idea of this is actually going back to the reason or the link that this power law has with standard viscoelastic models, and that this power law is really representing a spectrum of relaxations. So what you could conceivably do is to say that this is related to a standard generalized Maxwell model or Maxwell-Reichert model, and represent it as a series of parallel Maxwell branches. And each one of these Maxwell branches you can efficiently rewrite in a way that just depends on the previous time step, because it has standard time derivatives involved. So if you could approximate this derivative by something like this, then you'd be able to numerically work with these kinds of models. And so that's kind of what we did. We came up with this proposed definition, and the thing, again, we don't need to get too bogged down in the formula, but the key thing to note here is that basically all we need for this model is to know what the value of this Q, which is kind of storing our viscoelastic effects, is at the previous time point. And we need to have M of these, and this M represents the number of these branches of viscoelastic Maxwell models that we have. And so if you do some analysis, you can actually see how accurate this type of model is, and you can come up with these nice bounds here. And again, this is just telling us something about the error between this approximation and the true derivative. And it depends on two things. One is the series approximation. So how well does this Maxwell branch actually approximate the fractional model? And then the other one is the standard temporal discretization that you'd have whenever you take time steps. And the nice thing here is that this depends on the behavior of your function, which is pretty standard for these kind of error estimates, but it depends on this other value epsilon, which is basically how well do you represent a decaying polynomial by a series of decaying exponentials. And this is something that you can calculate in advance, and you can get a good idea of what the maximum error you would have would be. So the nice thing about this is, again, you end up with a computational cost that's standard for any forward in time problem, and your data storage cost is only then dependent on how many Maxwell branches you have. And what we did is we looked at how does this perform for real simulations. What you see is that all of the infrastructure and cost around solving nonlinear mechanics kind of trumps anything that happens with this viscoelasticity. So we saw very little change in the actual run times when you added in viscoelastic material models. So this is nice because it shows us we can use these types of models. But the other thing that is a really important question is whether we should. And there's a lot of different viscoelastic formulations that you can find in the literature. So just to walk through some of them, we can think of the classical Maxwell and Kelvin-Voigt models. And here, this SVE represents the kind of nonlinear viscoelastic PK2 stress. And then we have this SQ, which is maybe some component that you say has a rate-dependent influence on this viscoelastic stress. And then here SE is basically like an elastic branch. So we can make this analog to the spring dashpot, these classical spring dashpot models where this SQ is the dashpot component, and then the spring component in this case is this SE. Okay, so a generalization of these two is to have this sort of more generalized Zener model, where you basically combine these two, and by changing these parameters, this A1 and this B0, you can get back to either of these two forms. And so the fractional models are really just, again, a generalization of these. So if you think of this fractional Zener model, it would be pretty much the same as the Zener model, except for now we're allowing the derivatives to not be order 1, but to maybe be an order alpha, so some fractional order. And again, you can kind of connect these and make fractional Maxwell models and fractional Kelvin-Voigt models. And all of these things have been talked about in the literature for various applications. And when you look across the literature, so this is sort of, we try to compile different behavior we could see in different tissue types. So, you know, we have here artery, bone, brain, and so on, and over different experimental conditions. So uniaxial conditions, biaxial, compression, shear, relaxation, creep. You can see a lot of viscoelastic behavior across pretty much every biological tissue. And in most of these cases, not all of them, but in a lot of them, there was a model being proposed, and usually the model did a really good job of fitting it. And it was one of those models that I showed you on the previous slide. So there was a lot of reported success for a variety of these different experiments. But one thing that we kind of noticed is that usually the papers were focused on more or less replicating one experimental condition or protocol, or maybe just a few different ones. And so we thought that maybe it'd be worthwhile to take a more holistic look across all of the models and across all of the different types of experiments. So compression, shear, oscillatory shear, creep, relaxation, etc., and see how these models behave. And so that's what we did in this paper down here that we published recently in Journal of Elasticity. What we did is we looked at basically taking all the different classical forms, so these Kelvin-Voigt and Maxwell model and Zener models. And then we looked at all the different fractional forms, and we chose a few different fractional orders to look at. And then we varied different parameters that these models depend on. And then we basically, from that, could construct a bunch of different models. And we looked across all the different kind of tests that we see commonly in biomechanics literature. So what we ended up with was 4,216 models and 144 different test scenarios. And basically we simulated all of these to look at what the output would be in terms of the stress. And so we ended up with around 600,000 different simulated model outputs. And then what we wanted to do is to basically have a way of looking across these that would give us an indication of how the different models vary from test to test. And so for each test, we could create these color maps, which basically show us how similar or different models were. And we could then go across each test and look at how this sort of changed. And so in this color map here, the color is representative of the error, or the difference between two stress responses for a given pairing of models. So the rows here represent the different model forms that you can see in these color bars, and the columns represent, again, these different models. So the black on the diagonal is 0 because the model compared to itself has 0 difference. And this was interesting because it basically gave us a way of really doing en masse some interrogation of what these model behaviors were and how they tended to behave when you looked not just at one type of data, but at a range of different data. And I won't go through all of those details. It's a pretty long paper, but I'll just maybe highlight some of the key things that we saw. And so if we look at sort of the Maxwell, Kelvin-Voigt, generalized Maxwell and fractional models, you can see some interesting behaviors. So if we look at just cyclic stretch, so this is uniaxial stretch, then depending on the frequency, you get a very different hysteresis behavior when you look at Maxwell and Kelvin-Voigt. So if you see here, the red curve is this really large hysteresis area, and then at 5 Hertz, it shrinks. And the blue curve does the exact opposite. So it's got very little hysteresis, and then at 5 Hertz, it grows significantly. And so that might be the way that a certain tissue works, but most of the tissues that we saw didn't really behave that way. They tended to have a similar looking hysteresis loop as you changed frequency. And so you can see here that the green model, which is the generalized Maxwell, and the black model, which is the fractional model, these two both kind of maintain a fairly similar looking loop. The green one shrinks a little bit, but not as dramatically as, for example, the red one. Looking at relaxation, of course, you know, the generalized Maxwell and the fractional models both looked pretty good. But what was interesting was looking at creep, the relaxation behavior for these fractional models really stood out as having this sort of power decay, which is what we see most often in the different literature that we looked at. So I think that, you know, the question of whether we should use these types of models, the answer is that this type of model does seem to have some benefits if we're trying to have a robust material model that can cope with many different types of deformation, not just maybe the ones that we look at for a single test. Okay, so I'll jump in here and I'll talk now about the actual human myocardial model that we came up with. So this paper that we published in ACTA this year. So this model started or was really enabled by this really comprehensive paper from Gerhard Sommer and Gerhard Hotzapfel and Gratz, so the Gerhards. They published this paper back in 2015. And really what they were doing was trying to replicate a lot of the tests that had been done previously on myocardium, but to do it in human tissues and, you know, maybe revisit it with some more kind of modern understanding of how to do these experiments. And so what they had from from this paper was they did shearing in this rig they called the Triax. And what they would do is basically insert muscle tissue into this bath, which they could control the temperature, and they would do different shearing protocols. So they could do cyclic shear to varying degrees. So how much you actually shear, going from 0.1 to 0.5. And then they would do shear relaxation as well, where they basically go to one side and just hold it there. So you could oscillate the cube back and forth, or you could just shear it and watch what the stress response was. And since it's myocardium and muscle itself has a really hierarchical structure in order to give it the function it needs to kind of uniaxially contract, you end up with this anisotropy that you need to try to account for. So basically, depending on whether you stretch muscle fibers or shear them, has a different impact on the actual material response. So essentially, you end up with 6 different modes of shearing that you need to do in order to characterize the shear response for the myocardial tissue. So in addition to that, they also repeated the biaxial tests. They used their biaxial rig. They have an optical system, and they would mark dots onto the tissue, and they'd measure the strain over time and the forces. And so they do different stretch protocols where they would unload or load and unload up to basically 0.1 or 1.1 stretch. And they do this either equibiaxially, so they'd stretch equally in the fiber and the cross fiber direction, or they'd vary the loads in the fiber or cross fiber direction to varying degrees. They also looked at variable rates of loading and unloading, which give you additional data to compare with. So in total, this was a ton of data to work with, and all of it showed viscoelasticity. They had really good record of what they were doing in terms of the transient loading and unloading. So it was a great data set to think about modeling the myocardium. And so then thinking about viscoelasticity and fractional viscoelasticity, should we use it? We thought, okay, well, is there an argument to be made about why there would be a hierarchy of relaxation happening in the myocardium? And when you look at the literature and what people say in terms of viscoelasticity in the myocardium, people have pointed to many different elements of the myocardium. So this is sort of zooming in. This is the biventricular heart. If we zoom in on a tissue block, and then we kind of go in even further and look at local structure, people have said that viscoelasticity could come from the cells themselves. Could come from the coronaries, which are carrying blood through this tissue. It's heavily perfused. Maybe the extracellular space is responsible for the viscoelastic behavior, or maybe it's even just the extracellular matrix itself. And so this was interesting. I think there's probably some contribution from all of these factors, but thinking of the hierarchy, the structure of the myocardium and the extracellular matrix is very hierarchical. And so we started digging a little bit into that, and what you can dig up are some interesting experiments. This was an experiment done by Shen, where they're looking at the rheology of collagen fibrils themselves. And so they took these collagen fibrils and they basically stretched them and measured the stress response. And already there, they could see that the fibril itself was exhibiting this sort of viscoelastic behavior. So the fundamental architecture that holds your heart together is already viscoelastic. And interestingly, they couldn't fit these curves with a single Maxwell model. They needed two. So already you had two different Maxwell models that were required in order to get this sort of relaxation fit right. And the interesting thing here is that it really points to a different mechanism, I think, than what is usually thought about when you think of myocardium. And that's that the viscoelasticity is coming from some friction between molecules, as opposed to being driven by the fluid that might be in different components. So if you look at this and you think more about, is there a hierarchy of these molecular friction actions that might happen in the extracellular matrix, you can take the structure of a collagen fibril. So these are different alpha helices of collagen. And as you pull a fibril apart, you're basically pulling these collagen molecules apart from each other. And those will have some friction. Then fibril to fibril, you have proteoglycans, which are covering these fibrils. And they basically hoard water and they try to lubricate a little bit between these different fibers. But you'll have some friction there that's occurring between these fibrils themselves. And if you look at them, this is an example of all these fibrils branched out into single collagen fibers. And this is a cut through of another collagen fiber that's running right next to this one. And you can see that there's, again, another layer or level of interaction that could occur between these different bundles of collagen fibrils. And this keeps going. So if we look at decellularized SEM scans of myocardial tissue, so this is, I think, canine tissue, what we're doing is we're zooming in as we go from the right to the left. And what you see here in these little pockets, these are where myocytes would sit. And then there's kind of nested areas where you would have capillaries coming in, like right around here. You can see sheets that separate different layers of muscle. But all of this you can see is a very dense, highly structured layer of different collagen molecules, or collagen fibers, really, that are binding everything together. And so these interactions, I think it's plausible to think would be hierarchical, just based on the nature and the structure of the tissue itself. Okay, so what we wanted to do really was to see, okay, if we make a viscoelastic model, we know that it's important to look at multiple tests. So we wanted to try to look across the different tests that we had from this data set. And we wanted to compare really what you gain or lose as well with considering hyperelastic forms. So we wanted to do the same process of model fitting and parameterization to the viscoelastic model that we would do to some hyperelastic models. So we considered two different hyperelastic forms, and then we looked at a viscoelastic form. And so the two hyperelastic forms that we considered were the Hotzappel-Ogden model and the Costa model. And we don't need to get down into the details of what these different equations are, but I think the key thing to take away is that this Hotzappel model has this isotropic term, which represents sort of the base underlying matrix of the tissue in theory, and then it has these sums of additional anisotropic terms, which are telling you about how your material response, if you stretch fibers, you stretch sheets, or if you stretch across a fiber sheet, how does that add to, in the end, the stress, the PK2 stress that you observe? The Costa model in contrast is actually looking at very similar types of terms. So if you look at these, they're almost like the terms we see here. So they're exponential, they depend on invariance, but the main difference is that these are all multiplied together into one strain energy term, this kind of curly W, and that scales everything. So you get a separation, you get sort of different components similar to what you do in the Hotzeff-Ogden model, but in this case, you have a lot of coupling depending on what actions you do in other directions, how that might influence the stress response in another component. So these are the two models that we kind of use very frequently in modeling mechanics in the heart. And so those are the basis really of the model that we created. And the proposed model that we came up with is this one here. And basically what it is it's a sum of an elastic part, a viscoelastic part, which is this S star, and then this SP, which I should mention is in all of these models is representing the hydrostatic part. So we assumed in this paper that we had incompressible materials. So this SE, this elastic part, was basically like a simple Neo-Hookean type contribution to the PK2 stress. And then the viscoelastic part is actually, this S star is the solution to this fractional differential equation, which sounds scary, but it's actually, once you know how to approximate these time derivatives, then it becomes fairly straightforward. How do you basically restructure this like a normal forward in time iterative solution? So it's not too bad, even though it kind of maybe looks a little bit frightening. And this S star depends critically on this SV, which is the part of this model that is embedding all of the nonlinear anisotropic response. And the reason for that was mainly because when you look at the amount of hysteresis that you see, it really depends on how much you load and in what direction you're doing it. So we wanted to incorporate as much of the sort of nonlinearity into the viscoelastic contributions of the model. And so the form looks like this. And again, I don't want to, get too bogged down in the specifics of this, but I maybe will point to what I think is maybe the more key element to it, which is that we sort of borrow from both of the Hotzeff and the Costa models. So the idea here was to basically have some coupling between different components, similar to what Costa did, but to separate out the principal directions, so the fiber, the sheet, and the normal, from the sort of cross components, so the fiber sheet, the fiber normal, and the sheet normal. So we basically couple within the diagonal of this SV, and if we're in the local kind of fiber sheet normal structure of the myocardium, and then we have these sort of cross terms as well that are all coupled. Okay. And so what we did was we took some of the data to fit, and then we would use the rest of the data to do comparisons. So we looked at the 6 shear relaxation tests. We looked at 6 cyclic shear tests, and then 2 of the measurements from the equibiaxial. So this is one experiment, but we get a measurement in the fiber and the cross fiber directions. And we use these to basically parameterize all 3 of these models. And we did that by doing this parameter minimization. And this was our objective function that we were basically minimizing. And it's fairly standard. We're basically summing over all, we're taking norms over all time. We're normalizing the different contributions. And we're comparing basically the stress prediction from the model given a set of parameters here, which is represented by Y. And we compare that with the data. I think the one thing that maybe is not as standard is that we had this additional minimization. So this is the main minimization that we try to do. But we had another minimization based on this parameter beta. And what this was trying to account for the fact that we have all of these tests that were done, but they were done on different tissue samples and in different scenarios, different preconditioning environments. And so we may say that we know that the response should look something like what we see, but the absolute levels might vary from test to test. So basically, we broke the grouped tests of relaxation, cyclic shear, and equibiaxial stretch, and we said that basically the optimal model would give you the right shape of those models, but maybe it would be off by some scale factor because of the fact that it wasn't done on the same tissue. So essentially, we would minimize this chi, and that would give us a set of parameters, and then we could examine what these models look like. And so that's what we did. So we basically did a series of different tests here, and I'll just walk through some of these. So the first thing was the model fit. Sorry. And what we can see here are these plots are showing the model fits for the column here is the fiber sheet, and then this is the sheet fiber. So two components of this stretch, or sorry, this material response. So this is the top row is relaxation, then we have cyclic shear, and then this bottom row is the biaxial behavior, the biaxial stretch. These bar charts are showing you across tests what the errors looked like. So we have 6 bars for each of these because we had 6 different relaxation tests, we had 6 different cyclic shear tests, and we had 2 biaxial tests. And you can see what the errors for these different models were like. So the Hotzappel, the Costa, and the viscoelastic models. And what I would say is that, not surprisingly, all of the models kind of did a good job, I would say, so that you get a nice representation of the nonlinear effects from both the Hotzappel and the Costa model. I mean, they were designed to do this, so it makes sense that they would do a good job. And of course, the viscoelastic model gives you some viscoelastic behavior, so it should, ideally fit better. And it does. So it does a nice job of really fitting the data across a range of these different test scenarios. So we had pretty good agreement, I would say, for this model compared to the data. I think that maybe to point out where the two models, the two hyperelastic models, tend to differ, it's really in the biaxial response. So we could get a good fit to the nonlinear behavior in the cyclic shear and the biaxial test using the Hotzappel model. The Costa model tended to have this more shallow response in the biaxial test, so it couldn't get that sort of nonlinear rise in the stress quite like the Hotzappel model could. Okay, so the next thing we wanted to look at were the parameter space. So these plots here, these 4 plots are showing the objectives for a given test. So this is if we just focus on all the relaxation tests, this is the parameter space for that. And we can basically, in this case, we can break the parameter space up into 2 groups of parameters. One, which is a linear group. So basically, given a set of the nonlinear groups parameters, you can solve a classic sort of matrix problem in order to get the other linear parameters. So that's nice because you can then just look at a matrix and see, is it identifiable or is it singular? So you know whether there's a unique parameter set for each of these nonlinear parameters. And in this model that we had, that we proposed, there was only really 3 nonlinear parameters, this alpha and this beta, B1 and B2, which are the powers that we have in our exponentials. And so we could look across different tests. So relaxation, this is cyclic shear, this is the biaxial, and then this is all of the tests together. And you can see that really the relaxation and the cyclic behavior, neither of these give you a unique minimum. What you see is instead a range of parameters which would give you pretty much the same value. The biaxial looks a little bit better, but that's misleading because actually in this case, if you just focused on the biaxial data, you don't have enough information to set a lot of the parameters in the model. So this isn't sufficient in and of itself. Really what you see is that, again, combining all of the data gives you a much better idea of what's happening in these types of models. And you can see that it actually gives us a nice unique minimum for this material model. Okay, so we also looked at sensitivity. So just how do we have these how do these parameters depend? I might just jump a little bit here. I can see that we're running short on time. But essentially we looked at, if we have error in the material response that was measured, how does that change our parameters? And this kind of showed us what we'd like to see, that we have, if we have a 10% error, we get something 5–10% variation in the parameters. And changing parameters does have a meaningful impact on the actual error measure that we have. So we don't have any parameters that are basically insensitive to the tests we're running. Okay, so I think maybe I'll tell this result and then I'll jump to my conclusion slide. So one of the things that we looked at in this test was doing some predictions, and I think this is always a hard thing to do because a lot of times you have done all your experiments and you don't want to have to do more. But in this case, we were lucky that they did so many different experiments, so we could look at sort of splitting the data sets. And in this case, what we looked at was varying so not doing equibiaxial testing, but instead varying how much you load the fiber and the cross fiber directions. And the data that you see is down here. The solid curves represent the fiber stresses, and the dashed curves represent the cross fiber stresses. And the colors represent different ratios of loading, depending on whether you're loading more in the fiber direction or in the cross fiber direction. And what you can see is, which is really interesting here, is that if you go from this solid blue curve to this cyan curve, so basically we're changing how much we stretch in the cross fiber direction, you get a noticeable reduction in the response, the stress response that you measure. And similarly, if you look at loading in these red curves here, you see the dashed curve and the solid red curve, you get a very different response in the cross fiber direction because of the fact that you're loading the fiber direction. And if we look at these responses in both the Hotzeppel and the Costa model, they don't really capture that. In the Hotzeppel model, it makes sense because you have really separated the terms apart. So what you do in the fiber direction is really unique to the fiber direction. So if you add dispersion, which is something that people have done for these Hotzeppel models as well, you can kind of get a little bit more coupling, but you end up with an inability to fit the data. So it's sort of a trade-off, and you sort of ruin your ability to fit the data with adding the dispersion. The Costa model can kind of do that as well, but it gets hampered by the fact that it has to represent all of this data, and it's coupling everything together. And with the form that we proposed in this paper, it actually does a pretty nice qualitative job of matching this variable response that we see in the data. All right, so I'm going to skip. I'll jump ahead here. So just to conclude, I think that viscoelasticity is really present in all the tissues, pretty much under any experimental conditions that we have seen when we did our literature search. And fractional viscoelasticity is actually, it's not essential, but it's a convenient way of representing some of these more complex hierarchical responses that you see in certain materials that are really highly structured, like the heart tissue. We've shown that you can efficiently use these fractional models in a forward modeling context, and they actually seem to be quite important if you want to get a model that exhibits behavior that's sort of reasonable to a tissue, depending or irrespective of the loading scenario. So looking at creep versus relaxation versus stretch, shearing, etc. And then in this paper, we were able to develop a model that was leveraging the past hyperelastic forms to create this sort of viscoelastic model that did a good job of fitting the data and showed some good qualitative predictions as well. So I'll stop there, and I'll thank everybody in my team. This is a work that's been going on for quite a long time, and thank as well the key collaborators here, Gerhard Hofzeppel, Gerhard Sommer, and Ralph Sinkus.
Thank you very much, David. That was a very beautiful set of slides and very, very informative. I learned a lot. Questions from the audience? Any questions? If you can raise your hand. I see a lot of virtual clapping.
Adrian, both Francisco and Daniel have questions.
I was trying to look for where do I see raised hands. Daniel, if you want to ask a question.
Thank you. Hi, David. It's good to see you here. Thank you. Thank you very much for the talk. This was great. Absolutely. I guess my question is, I'm not an expert in viscoelasticity, but what I've seen in linear viscoelasticity, right, is that you can compute the stress tensor out of a convolution integral. And here, what you show us is that you have chosen to use a additive decomposition of the stress. So I guess my question is, what's the assumption, or how do you justify this additive decomposition in your model? I mean, splitting the elastic component and the viscous component.
Why can you this part here? Yeah.
Yeah, exactly.
Yeah. So we actually looked at a number of different ways to do this. So we looked at lumping this elastic part inside the S star, so the fractional part. So it'd be similar to the model that I showed here, where the fractional Zener. And there's some theoretical constraints that make that formulation, I guess, you have to be more careful. So because of the fact that you have that elastic contribution, you can end up with sort of reverse hysteresis. So you can create energy by unloading, which would violate thermodynamics. And so you need to be very careful about how you set those models up. If you split the model this way, that becomes very hard to actually recreate. So you can't get that scenario. So it's nicer in terms of the fact that it's harder to break it. But the other thing is if you look at the way in which these models behave in this sort of more high frequency, small amplitude space, and you look at frequency dependence, these two different forms behave differently. And that's where this one seems to have a better theoretical relationship to what we see from tissue than if you lump the elastic term here inside this fractional differential equation. So that was why we separated the elastic part out of here.
Okay, so it's based on a restriction from the theory. It's not based on physical grounds.
No, so actually, if we include it in there and we fit the data, we could actually get a pretty much as reasonable a fit as if we separate it out. So the errors between the two models, they both seem to replicate these two scenarios. But we're sort of, we can't extrapolate. We don't have the data to compare with at the sort of high frequency regime where maybe we'd be able to say one is better than the other. But theoretically, we know that this one is a little bit more easy to play with. The other one, you have to be a little bit more careful in terms of how you set it up. And so that kind of steered us this way.
Okay, great. Thank you.
Francisco.
Hi, David. Great talk. So I have a question also about that slide. So from what I see, your elastic part is isotropic. So what would happen if you load the tissue at a really small rate? So kind of that the viscoelastic terms are native, are not important. So would you get an isotropic response, or I'm missing something?
Yeah, so that's where so the fractional viscoelastic models like you have here, they actually exhibit viscoelastic response even when you slow it down. So it's not like a standard Maxwell model where you say, okay, if I just make the rate really slow, then that term is gone. These fractional models basically, that you still end up with hysteresis, even if you're slowing it down. So when we've played with this model, when you look at its linearization and you look at even a slow response, you'll still see some hysteresis. And of course, the other factor here is how you weight these terms. So again, it was more of a theoretical constraint adding in this elastic part here than a necessary constraint. So this A parameter, which scales the elastic part, is the smallest and the least important in the fit. And that's makes some sense because these fractional viscoelastic models actually are not purely viscous, but they're a kind of a combination of both elastic and viscous, right? So you actually get some elastic response sort of embedded in that model itself. And so you could drop this term. And again, doing so would increase the error a little bit, but not significantly. The reason why we don't do that and don't recommend doing that is, again, from a theoretical perspective, because of how these models behave around zero. So if you're trying to simulate them, you think about things like, okay, is the stiffness matrix going to be identified? Is it going to be singular or non-singular? And of course, you don't want to have a singular point in a material model. And so this elastic part really gives you that. It's sort of like in the Hotsaffel model here, if you knock out this isotropic part, all of these fiber terms basically die away at zeros and they have zero slope. So if you ran a numerical simulation where you said, okay, I have no isotropic term, then you'd end up with a singular Jacobian when you started the simulation, if it was started from rest, right? And it was the same thing we wanted to try to avoid with this model.
And another quick question. So the viscoelastic term, the form that you propose, does it come from an energy form? And do you have any requirements like convexity or things like that?
Yeah, so those are great questions. So the idea of hyperelasticity and relating it to sort of a strain energy, when you start thinking about the viscoelasticity, it seems like a less necessary way to formulate things because of the fact that those sort of hyperelastic functions don't really relate to the current energy that's in the material anymore. It's a more complicated formula. So it's not like you get this like easy relationship. But there are definitely questions about the local convexity of these models. And so what we did do in the paper was we looked at whether this model, if it was hyperelastic. So in principle, we could choose the fractional order alpha here to be 0, in which case we'd end up with a hyperelastic material. And the question is then, does it still work, right? Would it work as a hyperelastic model? And so we did look at the convexity of it, and it is convex. But it doesn't nicely collapse into a sort of classic hyperelastic strain energy like we'd see for the Hotsaffel-Ogden or the Costa model.
Okay,
but I'd argue that it sort of stops making sense to do that just because it doesn't relate necessarily to the current state of internal energy as clearly as it does in the hyperelastic cases.
Great, thanks.
Mm-hmm.
Wonderful discussion. Thanks for questions. I think to stick to time, we can continue talking, but I will officially end the sort of the scheduled part of the journal club. So thanks again, David, for the wonderful presentation. And then maybe we can potentially end the recording.
Yeah, I'll end the recording.